Welcome back, everybody, for another deep dive. Today we're going to be looking at computers,
Oh, very cool.
but we're going beyond, like the screens and the keyboards and the stuff you're used to, and like the programs, and we're really trying to dive in and understand like what really makes computers tick.
Right down to the nitty-gritty.
Yeah,
Yeah.
and our guide for this is W. Daniel Hillis and his book, The Pattern on the Stone.
Oh, excellent book.
Yeah, you read this one?
Oh, yeah, absolutely.
Okay, cool. So you're familiar.
Yeah.
So, one of the really interesting things that Hillis points out is that a lot of people think computers are about like circuits and wires and electricity and all this stuff, but he's like, no, no, no. You could theoretically build a computer out of anything.
Yeah, I love that about the book and about computers in general is that you can really abstract it away from the physical implementation.
Yep.
Like he actually built a tic-tac-toe machine out of Tinker Toys.
Okay, wait, stop right there. Tinker Toy computer.
Yeah.
I got to hear more about this.
I mean, it's not a full-fledged computer, obviously. It's
Yeah.
a tic-tac-toe machine, but still that proves the point that it's not about the electronics, it's about the logic.
Okay, so how does that logic work?
Well, it all comes down to something called Boolean logic.
Okay.
This is the fundamental language of computers, if you will.
Okay.
And it's built on really simple concepts like AND and OR.
Okay. I've heard of these.
Yeah, you can think of them like switches.
Okay.
Like imagine a light bulb connected to two switches.
Okay.
If either switch is flipped on, the light turns on, that's an OR gate.
Oh, okay, I get it.
And if both switches need to be on for the light to turn on, that's an AND gate.
Got it.
And it's incredible how these simple building blocks can be combined in countless ways to create even the most complex computer operations.
Yeah, that's kind of blowing my mind a little bit because, like, I'm looking at my laptop right now, and it's got all these, like, super complicated components, and I'm thinking, like, how does that relate to a light switch?
Yeah, it's all about abstraction. Like you said, we're going down to the nitty-gritty. And it really shows you that the universality of these concepts, like Hillis even suggests that you could theoretically build a computer using hydraulics. Imagine valves instead of transistors.
Okay, so, like, water
Yeah.
instead of electricity.
It wouldn't be very practical, but it just drives home the point.
Yeah, okay, I'm starting to get it, and I'm also starting to picture, like, a very wet computer, which I don't really like.
You wouldn't want that.
Yeah, but I get the point. It's about the principles, not the technology.
Exactly.
So, okay, we got this logic. How does a computer actually, like, take that logic and translate it into something it can understand and work with?
That's where bits come in.
Bits, so.
The fundamental units of information. Think
Yeah.
of it like a light switch that's either on or off,
Okay.
representing a 1 or a 0.
Okay.
That's essentially a bit.
Okay.
Everything a computer does, from storing data to running programs, boils down to manipulating these bits.
So, like, my entire digital life, like my photos and my music and, like, even this deep dive that we're recording right now, it's all just a bunch of ones and zeros.
At the most fundamental level, yes.
Wow.
It's pretty amazing.
Okay, so, and you were talking about that Tinker Toy computer?
Yeah.
So it worked.
It did work.
It played tic-tac-toe,
It played tic-tac-toe.
but it didn't have something that modern computers have,
It lacked one crucial feature:
which is,
restoring logic.
okay, what is restoring logic?
So imagine you're whispering a message down a long line of people.
Okay.
It's likely to get distorted along the way, right?
Yeah, totally telephone game.
Exactly. Restoring logic is like a built-in error correction system.
Okay.
It ensures that the signal, in this case, the information represented by the bits, stays clear and accurate.
So without restoring logic, computers would be, like, super unreliable.
Exactly. They'd be prone to all sorts of errors.
Okay, that's good that we have that.
Yeah, it's a vital part of what makes digital systems so dependable.
Okay, so back to this Boolean logic.
Yeah.
So, Hillis explains it. You can basically build any logical function, no matter how complex, using just those basic gates.
That's right. Those A and D or R are not Steat gates.
Okay, it sounds very Lego-like.
It is very much like Legos.
Okay.
You have these simple building blocks, and you can combine them to create incredibly complex structures.
So, like, my computer, for all of its, like, power and, like, all the amazing things it can do, it's really built on just, like, a foundation of these simple logic gates.
That's the beauty of it.
It's kind of like a digital house of cards.
You could say that.
Okay, and then this leads into another idea that Hillis talks about.
Finite state machines.
Okay, finite state machines.
You encounter them every day without even realizing it.
Okay, like what? Give me an example.
Like a traffic light.
Okay.
It has a finite number of states, red, yellow, green,
Right.
and it transitions between these states based on inputs like timers or sensors detecting cars.
Okay. Yeah, that makes sense.
That's a simple finite state machine.
Okay, so we got these finite state machines, but
Mhm.
Hillis also says they have some limitations.
He does.
Like he uses the example of recognizing grammatically correct English sentences.
Right.
Like there's so many possibilities.
Infinite possibilities.
Right, so like how could a finite state machine deal with that?
It can't.
You can't.
Finite state machines are great for simple tasks with a defined set of states and transitions,
Yeah.
but they can't handle the infinite variations found in language or really complex problem solving.
Okay,
That's where computers come in.
okay.
They combine finite state machines with memory.
Okay, so that's what makes computers special.
Exactly.
Okay, so we got the logic, we got the bits, we got these finite state machines.
We do.
So how does memory fit into all this?
Well, that's where things get even more interesting.
Okay.
That's where we really start to see the power of a computer.
Okay.
And that memory is like a, a vast warehouse just filled with storage bins.
Okay.
Each one has a unique address, and these bins hold the bits.
Oh, okay, so it's like each bit is like a 1 or a 0.
Exactly, those ones and zeros that represent all the information the computer's working with.
Okay, so it's like a giant digital filing cabinet.
You got it.
Okay. But how does the computer actually find like the right information at the right time?
That's where the memory addresses come in.
Okay.
Each storage location has its own unique address, like a street number or a postal code.
Okay.
So when the computer needs to access specific data, it uses those addresses to find it.
Okay. That's pretty amazing that it can do all that like so quickly.
It's a symphony of information, really.
Wow.
And it's all orchestrated by the computer's processor,
Okay.
which is kind of like the conductor following instructions from the program.
Okay.
But, you know, it's not just about the raw data itself.
What else is there?
It's also about how that information is represented.
Okay.
Like the same piece of information can be encoded in different ways.
Oh, okay. So like saying the same thing in a short, concise sentence?
Yes.
Or like a really long, rambling paragraph?
Exactly. And this leads us to the fascinating world of compression.
Oh, yeah, like zipping a file.
Precisely.
Okay, yeah, I do that all the time.
Yeah, those zip files, they're using clever techniques to reduce the number of bits needed to represent that same information.
Okay, but how does it actually, like, how do you actually make a file smaller?
Well, one common approach is to exploit patterns in the data.
Okay, so instead of repeating the same thing over and over again, you can represent it more efficiently.
Exactly like shorthand for data.
Oh, okay, I like that.
And Hillis, he brings up this counterintuitive idea about compression.
Okay, what is it?
He says that a picture of just random pixels actually contains more information than a picture of a face.
Wait, really? Because to me, it seems like random pixels are just noise.
Yeah.
But a face has all these features.
Right. It seems like it would be the other way around.
Yeah.
But a picture of a face has patterns, you know?
Okay.
Like adjacent pixels will probably have similar colors,
Okay.
but with a random picture, there's no patterns,
Okay.
so you can't compress it as much.
So randomness is actually like more complex in a way?
In terms of information, yes.
Wow. Okay.
And it highlights that information in the technical sense is different from meaning.
Oh, okay. That's interesting. So it's like the ingredients for a cake
Okay,
versus the actual taste of the cake.
I like that.
So the ingredients contain all the information,
Right.
but the taste is like the meaning.
That's a great analogy.
Okay, so compression isn't just about saving space.
No, it's also about efficiency.
Okay, how so?
If you can represent information more compactly, you can process it faster.
Oh, that makes sense.
And these encoding techniques have another important application.
What's that?
Encryption.
Ah, encryption. Okay, yeah, like keeping things secret.
Exactly, protecting sensitive information.
Yeah, like when I'm doing my online banking and stuff.
Exactly, you're relying on encryption to keep your credit card number safe.
So how does that actually work?
Well, one way is to use a shared secret key.
Okay.
It's a random sequence of bits that only the sender and receiver know.
Okay, so only they have the key.
Exactly, and that key is used to scramble the message so that anyone who doesn't have the key can't read it.
Oh, so even if someone like intercepts the message, it's just gibberish.
Exactly.
Okay, that's cool. And there are also those encryption schemes where you don't even need to share the key beforehand, right?
That's right. It's called public key encryption.
Yeah, public key encryption.
All right.
Okay, but how does that even work?
So imagine you want to receive a secret message.
Okay.
You publicize a key that anyone can use to encrypt a message for you,
Okay.
but you keep a separate private key that only you have to decrypt it.
Okay, so anyone can send me a secret message,
Right.
but only I can read it.
Exactly.
Oh, that's clever.
It's a brilliant system.
Yeah, very cool.
Yeah.
Okay, so we've been talking about like information
Yeah.
and how it's encoded
Right.
and protected.
Huh?
But what happens if like something goes wrong?
That's a great point.
Like, what about errors?
Yeah, with all this data flying around, what happens if a bit gets flipped or lost?
Yeah, what happens then?
Well, that's where error detecting and error correcting codes come into play.
Okay.
These techniques add redundancy to the information.
So it's like having a backup copy.
Yeah, or a checksum to ensure its integrity.
So it's like a safety net for our data.
Exactly.
Yeah.
One simple example is a parity bit.
Parity bit, okay.
It's like adding an extra bit to a group of bits to make sure the total number of ones is always even or always odd.
Okay.
If a bit gets flipped, the parity check will catch it.
So it's like a spell checker for data.
You could say that.
Okay, what about errors in the actual computations themselves?
Ah, very good question.
Yeah, like what if the calculator is broken, not just the numbers that I put into it?
Exactly. And that leads us to the concept of fault tolerance.
Okay, fault
A
tolerance.
whole other fascinating aspect of computer design.
Yeah,
So you're asking, like, what if the calculator itself is faulty?
right, exactly.
Not just the numbers you're putting in.
Yeah,
That's a much trickier problem.
it seems like it.
But engineers have come up with some pretty clever solutions, often inspired by nature itself.
Oh, okay.
One approach is to build what are called fault-tolerant logic blocks.
Fault-tolerant logic blocks.
Yeah, it's like having backup systems in place so that even if one part fails, the others can keep things running.
Oh, okay, so it's like having multiple engines on an airplane.
Yeah, exactly.
Like if one fails, the others can still keep the plane in the air.
That's a great analogy.
Okay, cool.
And this idea of redundancy is really central to a lot of fault-tolerant designs.
Okay.
Like, you could have multiple copies of the same logic block and then use a voting mechanism to determine the correct output.
Oh, okay, so like if one of them gives a wrong answer,
Right.
the others can outvote it.
Oh, that's cool. It's like a panel of experts
Exactly.
where the majority rules.
Yeah.
Okay, so we can build these systems that are more tolerant to failures.
We can?
But Hillis says that one of the biggest challenges is actually the software.
He's absolutely right.
Yeah.
Software can get so complex.
Yeah, millions of lines of code.
Millions of lines of code.
All interacting. It's really hard to predict how it's all going to work together.
Yeah, and that's where bugs come from, right?
Exactly.
Those little glitches.
Yeah, those pesky bugs.
Yeah.
And they can be caused by simple oversights or misunderstandings,
Yeah.
or just the sheer difficulty of trying to think of every possible scenario.
Yeah. It's impossible to think of everything.
It's like finding a tiny crack in a giant mosaic.
Yeah. So computers aren't as perfect as we think they are.
Well, perfect they are not.
All right.
They are creations of human ingenuity.
Yeah.
And like all human creations,
They have flaws.
they have flaws, exactly.
But Hillis doesn't just like point out the problem.
No, he doesn't.
He offers some ideas for solutions.
Right.
And this is where he brings in the idea of taking inspiration from nature.
From biological evolution.
Yeah, exactly.
He argues that this traditional engineering approach where everything is so hierarchical,
Oh,
it makes these systems inherently fragile.
okay.
It's like building a house of cards.
Right, one wrong move and the whole thing collapses.
Okay, but biological systems,
Like our brains.
Like our brains,
Yeah.
they're much more resilient. They
Yeah.
can adapt to damage, they can learn from mistakes, they can even rewire themselves.
So he's saying we should look to nature to design better computer systems.
That's the idea.
Okay.
He even proposes this radical idea called simulated evolution,
Simulated evolution.
where you essentially breed computer programs.
Breed computer programs. Okay, hold on.
Yeah, like we breed animals for specific traits.
Okay, so I'm picturing like a digital farm where computer programs are running around.
Yeah, you could picture it like that.
Okay, so how does this actually work?
So you start with a population of random programs,
Yeah.
each one designed to solve a specific problem,
Okay.
like sorting numbers or recognizing images.
Okay.
And then you test them
Okay.
to see how well they perform.
Right.
And the best ones are selected as parents
Okay, parents for the next generation.
for the next generation.
Okay.
And then you create new programs by combining elements from the parent programs
Okay.
and introducing random variations along the way.
So it's like survival of the fittest,
Yeah, exactly.
but for computer programs.
Exactly. And this process just repeats over and over again.
Okay.
And each generation gets better and better at solving the problem.
So the computer's basically learning through trial and error.
You got it.
Oh, that's so cool.
And what's amazing is that this approach can lead to solutions that are completely unexpected.
Oh, wow.
Solutions that no human programmer would have thought of.
So we're essentially like harnessing the power of evolution to write software that's like beyond our capabilities.
You could say that.
That's crazy.
And this idea, it's not limited to simple tasks.
Okay.
It could revolutionize how we design all sorts of complex systems.
Like what?
self-driving cars,
Oh.
robots that can learn and adapt.
Wow. Okay, that's pretty mind-blowing.
Yeah.
But it also kind of makes me think, like, if we can evolve intelligence in a computer,
Yeah,
what does that tell us about our own intelligence?
that's a profound question.
Yeah.
And it's one that Hillis definitely wants us to think about.
Yeah.
He reminds us that our brains are themselves products of evolution.
Right.
We're not the result of some grand design.
Yeah.
We're the culmination of billions of years of trial and error.
Wow. Okay, so our brains are more like a messy, evolving ecosystem
Yeah,
than like a perfectly engineered machine.
that's a great way to put it.
Yeah.
And that messy organic structure is
Yeah.
part of what makes our brains so adaptable and resilient.
Okay, but it also makes them hard to understand.
Incredibly difficult to understand.
Yeah, every time we learn something new, it just seems like more questions pop up.
That's the beauty of science.
Yeah.
It's a never-ending journey of discovery.
And as we explore computing,
Yeah.
we're not just making new technology.
We're learning about ourselves.
We're learning about ourselves.
Yeah. It's a journey that takes us inward and outward.
Yeah, both at the same time.
Exploring the nature of intelligence.
Yeah, artificial and natural.
Well,
Okay, so I think this has been a really fascinating deep dive into computer fundamentals.
I agree.
We've explored all these really cool ideas,
We have.
and hopefully it's given everyone some new things to think about.
I hope so.
So to all our listeners out there, next time you're on your computer, take a minute to think about all the amazing stuff that's happening behind the scenes.
All that logic and information and innovation.
Yeah, it really is incredible.
It is.
And until next time, keep those brains buzzing.
Keep thinking.